In the previous lectures, we have been talking about the traveling salesman problem. We have been implemented the problem with the help of recursion, and in this lecture, I would like to show you the stack memory related visualization of the problem. So the problem is that we have a graph like this, and we would like to find all the Hamiltonian cycles. You may pose the question, why? Because of course the solution for the traveling salesman problem is a Hamiltonian cycle with the lowest sum of edge weights. Okay, so we have the source code something like this. I just created a universal code, so it has nothing to do with Java, it has nothing to do with C++ or Python. This is the core of the algorithm, so this is exactly what we have implemented in the previous lecture. So we have a graph 0, 1, 2, 3, 4. So we use integer representation for the vertices, and we have a stack memory. So whenever we call a given function or a given method, then the programming language is going to store that given function call or method call on the stack memory with all the local variables. And whenever the execution of a given function is over, then that given stack frame is going to be removed from the stack memory, and the flow of control will return to the previous function call. Whenever we use the return keyword, then what's going to happen? In these cases, again, the programming language will backtrack to the previous stack frame, so basically the previous function call, so basically the actual stack frame is going to be discarded. So let's take a look at what's happening under the hood. So we call the traveling salesman problem, the actual position is equals to 0 and the counter is equals to 1. So the counter is going to count the number of iterations and the actual position is going to track the actual vertex. Every single vertex has a given integer representation, so 0, 1, 2, 3, and 4 as you can see. So what do we have to do? First of all, we have to check the base case. The counter is equal to the total number of nodes. Of course not, so we keep going, and what do we have to do? We have to consider all the vertices in the graph, and we have to check whether that given vertex is valid or not. So what does it mean? A given vertex is valid if we haven't been considered that so far, so if the given vertex is unvisited, and if there is a connection between the actual vertex and the vertex with index I. So basically we have to consider all the vertices. Of course we have considered the first vertex, so we consider the next vertex. Is it a valid vertex? Of course. First of all, because it is unvisited and because there is a connection between the actual vertex and the vertex with index I, as you can see. So what do we have to do? We have to set it to be visited, as you can see, and we have to call the traveling salesman problem function recursively with I, where I is equals to 1 and counter plus 1. So this is why another stack frame is going to be inserted onto the stack memory with values 1 and 2. So we start again, the actual position is equals to 1, the counter is equals to 2. Of course, the counter is not equals to the total number of nodes. The total number of nodes, of course, is the number of vertices, 1, 2, 3, 4, and 5 in this case. So we keep going. What do we have to do? We have to consider all the vertices in the graph, and we have to check whether adding that given vertex to the solution is valid or not. Of course, vertex 0 is already being visited, so it is not good. Vertex 1 is already being visited, so it is not good. But vertex 2 is working fine because it is unvisited and there is a connection between the actual vertex and vertex with index I. So we set it to be visited, and we call the traveling salesman problem recursively with I and counter plus 1. Okay, so because of the recursive function call, there's going to be another stack frame in the stack memory with value 2 and 3. So again, we have to check whether the counter is equal to the total number of nodes. Of course not, so we have to consider all the vertices in the graph. The 0 is not good because it has already been visited. Vertex 1 has already been visited. Vertex 2 has already been visited, but vertex 3 is a valid vertex because it is unvisited and there is a connection between the actual vertex and vertex with index I. So we consider it to be visited and we call the traveling salesman problem recursively with I and counter plus 1. Okay, so we start again. The counter is not equal to the total number of nodes, so we have to consider all the nodes of the graph. 0 is not good, 1 is not good, vertex 2 is not good, 3 is not good, but we can consider vertex 4 because it is connected to the actual vertex with index 3 and it is unvisited. So we set it to be visited and we call this function recursively with I is equals to 4 and the counter equals to 5. As you may guess, if we consider the first parameters, these are going to form the valid Hamiltonian cycle if possible. So for example, in this case, because we call this function recursively, we have to check whether the counter is equal to the total number of nodes. Of course, because the total number of nodes is equals to 5, the counter value is equals to 5, and we have to check whether the last node we have considered, vertex 4, can be connected to the first node. And of course, there is a connection between the last node and the first node, which means that we have found the first Hamiltonian cycle. You may pose the question that, okay, how do we know that we have to include 0, 1, 2, 3, 4 and 0 in the Hamiltonian cycle? And basically, as you can see, 0, 1, 2, 3 and 4. So the first parameters are going to define the Hamiltonian cycle itself. Okay, and of course after that we have to return. What does it mean? Whenever we use the return keyword, the programming language is going to remove the actual stack frame from the stack memory and going to backtrack to the previous function call. So in the previous function call, we have called the traveling salesman problem here. So we backtrack here, and what do we have to do? We have to set the vertex with index I to be unvisited, so the visited variable to be false. So what does it mean? We set vertex 4 to be unvisited and the actual position is equals to 3. So, because this is the end of the given function, because we have considered vertex 1, we have already considered vertex 2, as far as this for loop is concerned associated with vertex 3, we have already considered vertex 4 as well, so this is the end of this traveling salesman problem function call. So what's going to happen? Whenever the programming language considers the end of a given function, it is going to remove the actual stack frame from the stack memory and backtracks to the previous function call. So this is why we backtrack to TSP with values 2 and 3. So what does it mean? That we backtrack to this location and we set visited I to be false. What does it mean? We set vertex 3 to be unvisited again. Okay, then in this case we have to keep going with the for loop. We have already considered vertex 3, but we have another option as far as vertex 4 is concerned. So we consider vertex 4, it is working fine, so we call the same function recursively with values 4 and 4, and then we start again. Of course, the counter is not equal to the total node, so we keep going and consider all the vertices of the graph. 0 is already being visited, 1 is already being visited, 2 is already being visited, 3 is going to be a good option, so we set it to be visited, and we call the function recursively. So there's going to be another stack frame, and as you can see, 0, 1, 2, 4 and 3, it is going to yield the Hamiltonian path so far. Okay, of course the counter is equals to 0 in this case, but the last node cannot be connected with the first node. So there is no direct connection between vertex 3 and vertex 0. So what do we have to do? We have to consider all the nodes in the graph one by one. Is it a valid node? Of course not, because we have already visited vertex 0. We have already visited vertex 1, vertex 2, vertex 3, and vertex 4. So this is the end of this function call. What's going to happen when the programming language considers the end of a given function call? The actual stack frame is going to be removed and the programming language will backtrack to the previous function call. So we backtrack to where we have called the traveling salesman problem recursively, and we keep continue with the flow of the application. We set visited I to be false. So what does it mean? The last node we have considered, we set it to be unvisited, and this is the end of that given function. So again, we backtrack and remove the stack frame from the stack memory and backtrack to vertex 4. This is the location where we backtrack, so we set visited I to be false, so we set the vertex 4 to be unvisited, and we backtrack to vertex 2, so another stack frame is going to be removed from the stack memory, and we have to backtrack again because we have already considered all the neighbors of 2. So what do we have to do? We have to backtrack to vertex 1, and in this case we have one more option. We have already considered 0, we have already considered 1, we have already considered 2, but we haven't considered vertex 3 when dealing with vertex 1. So we have no other option but to consider vertex 3, okay, and then we have to call the function recursively. So recursive implementation is quite a long procedure. Okay, so we have to consider 0, it is already been visited, 1 is already been visited, 2, we haven't considered 2 so far, so we set it to be visited and we call the function recursively. Okay, there's going to be another stack frame, so what do we have to do? We have to start again. The counter is not equal to the total nodes, so we keep going and consider all the nodes. 0 is not good, 1 is not good, 2 is not good, 3 is not good, 4 is good, so we set it to be visited, and we call the function recursively. So what's going to happen? The counter is equal to the total nodes. The last node can be connected with the first node because there is an edge between vertex 4 and vertex 0, so we have found the next Hamiltonian cycle, 0, 1, 3, 2, 4, and 0. You may pose the question, how do we know the order? 0, 1, 3, 2, and 4, as you can see. And of course, we can connect the last node with the first node, so this is why we append another 0. After that, of course, we have to return, which means that this stack frame is going to be removed from the stack memory. We backtrack up to the first node, and then we consider the vertex 4 instead of vertex 1. So we are going to consider 0, 4, 2, 3, 1, and 0 as another Hamiltonian cycle. And finally, we will consider the last Hamiltonian cycle as far as 0, 4, 3, 2, 1, and 0 is concerned. Okay, so that's all about the visualization of the traveling salesman problem as far as the recursive function calls and the stack memory stack frames are concerned. As far as I am concerned, I found these kinds of visualizations quite useful. So I hope that you find it useful too. Thanks for watching.